Welcome, I'm Bill Wake. We're here working on a programming language called 10th that's sort of a subset of 4th. And lately we've been working on some tests involving the dictionary, and I'd like to refactor those dictionary macros. And if we get that done, I'd like to move on to recursion and make sure we can handle that properly. All right, let's test up our to-dos. Let's see, 14. Wow. All right, so refactor dictionary macros. That's what we want. And let's see them. Oops. So they're in core-test.macros. All right, so you have dictionary start, and you give it the label that you're going to write these things into. The dictionary start just sets up x0 as the pointer to the slot where you're going to write. Then dictionary add is going to add the next entry. For us, at this point, an entry is just the address of a procedure. We haven't linked in the name and the linked list that we expect to use later. And notice it updates x0. Basically, it adds 8. So it loads the entry address into x1 and then does this sort of dereference of it and then stores that in the next slot. Now, I think what's missing, and let's just go to an interpreter test. Oh yeah, here we go. So we realized to make this work, we had to have the header values. So we have both start2d as the address of routine, and then start2d header is a memory address pointing to it. And then we store that into the 1. So it gets it into the slot at that point, I guess you'd say. So my contention or my belief is we should be able to do this in one go and not need to worry about this start2d header. Okay, so start2d. Well, let's expand out our macro. Okay, and I'm just going to play with this secondary call secondary test because it seemed to be the most sensitive to this. So the push header here, I'll just put that there like this. And entry is going to be push header. Okay, that should give no change. Interpreter tested out. Secondary call secondary still passes. Okay. But if I move this down to where it's being used, well, x0 is not a good choice, is it? Because it's being used by the dictionary. Well, the dictionary macros assume x0 points to the right thing, and we're using it for something else here. So let's use a different variable. Let's just do x4 for x0 and x3 for x1. Okay, just so we don't break things. All right, again, I'm just going to do those little small steps. Okay. And then let's move this down since nobody references. Whoops. Start2d. Oh, that was the one choice we shouldn't worry about. Let's do the same thing for this one. x4, x3, x3, x4. So we'll do push. Okay. So you can see we're writing into push header the value of that, and then we're loading it. Well, yeah, we're loading it from that memory address. So there's duplication there. All right, let's make sure this is good. And I'm going to comment these three out. And actually, I don't know that we need that start 2D header stuff either, but let's check that out again. Start 2D header. Start 2D label. Okay, we probably use that there then. All right. That's commented out. Just do another make. All right, good still. Handy, it's the last test. All right. So that seems legit. All right. So now let's optimize this a little bit. So we load the address of push. And we store it into push header. Well, it seems just as good to store it in X0, doesn't it? Am I jumping too far? Let's say we didn't do anything with it. I don't know. So, like, wouldn't we have done this already? Somewhere we messed up. Maybe when I was doing so much indirection. But I think this might be it. Load address X4 push. I think this should become X1. And then that address should be sitting in X1 at this point, and we're going to store that address into the location we want. That seems right. Do you think I need the indirection? You could well be right. Okay. Let's put it back in and see if it acts different. No, it doesn't like it. Okay. I think I did add this indirection when we were I was lost in the levels of indirection, not realizing that I needed that one level less on my start 2D. This seems okay. So I should be able to take this label and just do that. All right, I'm going to make a new one. I don't want to break everything, so I'll make a new one and then rename it at the end. Okay, this is dictad2 entry. So we load the entry, we store it x1, x0, pound 8, right? Load the entry, store x0, x0, pound 8. Okay. So I think this is equivalent to dict2 push. I'm going to take these out because they didn't appear to be needed, but I'll leave these two commented. Okay. So I'm making this new one because I don't want to break every test out there because they all assume there's that extra level and they didn't do it right and all that. So let's not break it. Okay. There's just a weird little bump in the screen when I do this, so I'm worried that something's not running right, but it seems okay. All right, so that seems good. So let's modify the rest. Well, that's not much. And 2. Dictad 2. Okay. Yeah, I think, well, no, the start 2D is in the secondary start. So, but yeah, there's some combination of that wasn't quite right. Okay, but this seems okay. I think this is the only one in here. Yeah. All right. And then the other ones, I think were in here. Okay. Well, we'll do them one at a time. I'm just going to call these dictad2s with no header. Okay. All right. And that was core tests. If 0. Okay. All right. Well, now I'm kind of confident. No, I'll do it one at a time. Let's be careful. You know, working in assembly is just that much riskier to mess up. Okay, so there's that one. I'll go ahead and move this one too. And I think this is enough. Okay, everything's good. So let's commit this. Revise dictionary, add macro to dict, add 2. Good. All right, and now we're going to take the macro, take this one out, rename this one. Deal with the renames here and here. Okay, yep. Yeah. Okay, good. Well, that took a lot less time than I was afraid of. But I think pulling the macro in and then kind of manually optimizing it, I think was a good technique. I'll have to keep that one in mind. I want to mention something else I did just off camera. I went and added a little better comments to these things. I think there's still ones I missed, but I'm trying to say which registers are affected and what do they do and stuff like that. So that may look a little different. Oh, and then I think this is dead code. I'll just delete that. Okay. And then there's one more change I wanted to make. We have something called if true. I believe it's in our core. Yeah. I think that has been confusing to me every time I look at it. And I mean, I worked in compilers a long time. I know the semantics of an if statement, stuff like that. But, I think this thing it's called if true, but I think really what it is jump if false. So it compares, and if it's 0, which is false, it jumps to the address that we're pointing to. So I'm going to change this name. Let's search for it first. I don't think it's used that much. A few tests maybe. Okay. Let's tackle these. I'm gonna just do it directly. Let's see. So we did this. I guess I'll say simplify. Oh, I got to take out code for that stuff too. All right. Before I do the jump if true, rename jump to jump if false. And this is not jump, it's if true. Okay. All right. So let's finish the refactoring on this. So interpreter tests now no longer needs this stuff. I think. Good. Okay. And then I don't think we reference them either. These. Okay. Same thing for core tests. Oh, I'm so happy to delete this. When you see it propagated, you really see how much it costs you. Okay. blocks. Well, let's do it slowly. Okay. I don't think those are referenced. Nope, they are. Okay. Some of them are, and some of them aren't. Or something. We got a bus error. Well, that's the only reference to that one. Who had the bus arrow? If 0. Okay. That's not referenced. That's not referenced. Okay, so it's one of these two. The thing is, if the label weren't there, it shouldn't notice. I mean, it would complain if it wanted to use it. Well, that's one match too. What the heck? Okay. I feel like something went weird there, but all right. Okay. Oh, did I do it? Oh, I'm sorry. Yeah, sorry. Gosh, I don't know. At some point, maybe I should find a way to get the chat window visible here, but it's tricky. I see people do it, but gosh, I like to have the screen. All right, I'll try and check better. All right. Yeah, so was there anything else with that? I think that's okay. All right, so now, yeah, let's go to this. Rename if true to jump if true. Okay, I guess that can stay. This is jump if true. And I don't know, I think this might be better in that order. Oh, jump if false, right? Okay, we took that out. Didn't we have one here? Oh, there it is. Okay. If I've done this right. All right. Good. Okay. I'm feeling much better about this. Okay. All right. So the big task I want to do is handle recursion. Let's see. I've got a slide for that. And I think what we're going to have to do is we're going to have to add some more primitives to make this thing happen. But here's my version of the factorial. X factorial equals x times x minus 1 factorial. All right, and so I've used comments on the side here to kind of say what's the stack look like, and the front of the stack is right after the arrow. So the factorial method is going to take a stack with one, well, it's going to work on the top of the stack. Okay, so we'll duplicate that, and then we'll push a 1 and call not equal, which basically takes 1 versus A and decides if they're equal or not, and leaves a Boolean on top of the stack. Then the if consumes that Boolean, and it either continues to the dupe or it jumps around to the end. Okay, if it jumps to the end, we've got the original value on the stack still, and that was 1. We just checked it, and 1 factorial is 1. So we kind of get the exit case for free. If it's not a 1, then we're going to duplicate it. So we'll have, say we're doing 3 factorial. We'll have 3 on top of the stack, then we'll push a 1 and subtract. So we'll end up with 3 minus 1 on the stack, which is 2. And we'll call factorial, which takes the top thing on the stack, which is 2. And it leaves 2 factorial on the stack when it comes back. So we got 2 factorial on the stack followed by 3. And then we multiply them. So 3 times 2 factorial, which is 2, is 6. And we fall through to the end. And there we have the value we're after. So the problem with that is we don't have dupe, we don't have NE, we don't have sub, and we don't have multiply. So we've got 3 or 4 primitives to add before we can really plug in our refactoring recursive factorial thing. All right, there's also a little weirdness around that recursive call because, right, we have to make sure we've defined it enough that we can call it. Now, fourths, at least the book I had required that you could call a recursive routine, but you can't have mutual recursion because you won't know, you don't have forward definitions or forward references, I guess. I don't know if that's, I guess I can live with it. We don't really care. You could play some tricks, like you could make some sort of declaration that says, here's a method name, but body to be defined later or something, that kind of thing. All right. So I guess what I think I'll take away is we got to do dupe, not equal, sub, and multiply. All right. In here. Dupe, not equal, sub, and multiply. Okay. And once we have those, then we can put in our routine and check it. Create symbols when adding a dict. Yeah, I really wish I could. Oh, it's so annoying. But I think once we have recursion done, and then I kind of trust our interpreter. They call it the inner interpreter because it's kind of the core language interpreter. I will trust it at that point, hopefully not unjustly. With that done, I think almost everything else we do, we can probably, well, if we implement the parsing and all that stuff, the quote outer interpreter, then we can use that to test almost everything else. And I think that should go pretty quick like that. With these others, there's a little bit of work to test them. All right, but we'll jump in. Dupe. Okay, so core, where's the other push? Yeah, there's push. Okay, dupe's a close friend of push. Let's just stub it in. This is a user visible word, so I'm not putting the underscore. Oh, we already have add. We don't have multiply. All right. Dupe, and we'll just do a return for now. And let's specify it. Dupe, duplicate the item on top of the data stack. Input x19 VSP points to top of stack. And then I'll just say the output is x19. Well, no, it's two things really. Stack has top element duplicated. x19 increased. All right. And I think for this, we don't have to have all dictionary headers and all that stuff to test this, because this is just a little core routine. It's not calling other methods. It's not doing anything fancy. So just like we didn't for add, we won't need a fancy test for this. Okay. Let's see, core tests. Let's go find the duplicate test. Push. Wonder what that is. Well, we'll put it here. Okay, so test start, and we're going to say duplicates top item. And test end. Okay, so we'll have to set some VSP. We had a push test stack. Where's that? Let's move that up, and we'll make this a data segment again. Start. Okay. Data. Text. Okay, so we've just got some stuff. All right. Now that seems okay. L data. Okay. What address? Okay, so X19 is the proper data virtual stack pointer. All right, and then address X20 test data. Let's move this up too. Okay, so I think this is the same for us. Okay, so we are pushing L data, which has 142, onto the stack. Okay. And now we want to call dupe. So let's at least put my range in it. All right. What are we going to assert? Well, we have a pop data, right? Is that core or that's a macro? I don't even think it's a. I think it's a no, not Unix functions. Core, no. Data pop. Assembler.macros. Okay, so there's data pop. Loads this from there. Okay, so our test should say, well, I think, well, one thing would be yeah, I think I'm going to define this macro I want. Data pop AB. Okay, so ABC are sort of the the normal names for the top three elements. And I think we'll adopt that. So I'm going to assume there's a macro that's going to put x0 is A, x1 is B, the first two elements off the stack, pop them in. And then given that x1 is that, we really want to save it. And I think we used x28 before. Now, so let's move x28 equals to x1 and call move x1 gets 142, like you say, and assert equal, and then move x28 to x0, move x1 gets 142 again, and BL assert equal. Okay. Right. Let's see how that goes. Let's put this in the list of tests to run just for... Okay, that's core tests. Core. Whoops, I didn't define data pop. Should I put the registers? Yeah, that's a good idea. Except I do want this macro. Let's go back to core tests. Okay, so yeah, so you're suggesting move. If we did this, x1 be able to assert equals. I think we also have to save. Assert equals allowed to chew up x1, so we're gonna have to save save the value somewhere too. Like that. Okay, so we'll pop x0, x1. We'll move x0 to x28, so it's duplicated. We'll check that x0, x1 are equal. We'll restore x0 and then check that it's really 142. Okay, I like it. Pop AP, register 1, register 2. Okay, I think that's good. Well, okay, let's see if that works then. The test should fail, but the macro should be there. Okay. Oh man, so sorry of doing that. X20 L data. Core test S42. L data. Unknown arc 64 figures of kind. Do we have to do a load address? Oh, we did move this. Oh, this wasn't in the data section before. It's constant, so it can be there. All right. Dupe. Okay, good. Now, core, we put this for dupe, but we haven't exported it. All right, now the test should fail. Good. All right, a nice clean failure. It would be nice. Well, I would love to extend our assembler unit. Okay, so core tests, push does nothing, dupe does nothing. Okay. I don't know the right way to do this. Well, sort of the easy way is data pop x0, data push x0, data push x0. Okay. Core. Oh yeah, let's use our top. Thank you. Data top gets x0. Saved instructions already. Now that's how TDD is supposed to work. It wasn't that hard. Okay. All right. So we've got ACP and a dupe primitive. Okay. Now this pop. This I think we could express it more simply like this. Data pop register 1. Okay, let's make sure that's all good. All right. Now, what else do we need? It's open to me if this should really be called data pop A. But I guess it's okay without it. But I do think we had another test that could use it, right? Add data pop. This could do data pop. Well, we really should data pop. X1, X0, okay, is what we have. Is that, well, A, B plus, I mean, yeah, A push something plus should really take the second entry and drive from that. We don't care for plus and multiply, but divide and subtract will need it. Okay, so I guess that's okay. If I do AB. Plus passes, okay. Did plus make add. That is good. So we've done dupe. And actually, I think any is a little harder. Let's do these. Multiply is probably a little easier than sub. Maybe not. Okay. Let's see. Sub. Well, we'll add a stub first here. And these are stack. It's arithmetic. That's that. Okay. Global sub. Replace two values with be a little more. Okay. I'll leave this because it's known wrong. Yeah, we could negate. I wonder where somewhere I had a list of words I wanted to do. Let's see what I called. Negate. Vocabulary. Neg. Okay. Yeah, let's do neg then. Well, neg's a little harder, right? Let's come back to it. I think I'm going to take the expedient way now, and then we'll come back and there is a sub. Yeah, maybe just to do less primitives, we'll do it with sub. All right. We need a test. Sub b minus a is difference. I don't know, this should probably, yeah. Okay. Okay, I think we're better. Oh, we have data. Okay. I guess our data is still... Where's L data? Up here, 142 and 58. Okay, so if we push 142 and push 58... Okay, this is the same. That felt Okay. Can I do this? Am I addressing those? It's B minus A. So if you want 3 minus 2, you push 3, push 2, and then execute minus. Okay. There's an addressing mode. Immediate offset, that's the one. RN pound value. Oh, that's not going to work. None of those look attractive to me. Can I say this? Push, push. And then I think our we should be able to do a data pop. X0 move X1 gets 142 minus 58. Is 4. 14 minus 5 is 9, but it's 1 less, so it's 8. 84, does that sound right? No. 84. 62, yeah, 84. Yeah, maybe it needs a pound sign. I don't know. All right. We load this. We initialize the stack pointer. We load data index 20 and run push. Push needs an X20 because usually when you're doing this, you're working your way through a secondary. Okay, same thing here. +8. Get the next entry, push that, subtract, and then make sure the result is X0 is right. Okay. This should fail. And I think it should fail. Oh, darn it. No. There we go. I don't know when you use pound or not pound. It's just not clear to me at all. All right. I think it's because it's, I don't know. Make up a reason. Okay. That's failing. And we know why it's failing because we do an add and we think we should do a sub. I think it's called sub, so that should make it pretty easy. I guess this is popped. Okay, good. All right. sub, and then multiply. And I guess I could wish for parameterized tests, but we'll live. Now, I'm not as sure how multiply works, because multiply can generate numbers bigger than a word. And therefore it can have overflow and all that. I don't know that I want to worry about that. It's funny, you can say multiply, you can say times, you can say the product. All right. And again, that's going to fail because it's producing the negation rather than, oops. And let's add a test. All right, I'll just take this for starters. Oh, I already did. Okay, we'll load those two numbers. We'll call mul. And 142 times 58. $82.36. How many times a day am I going to do this? Okay. Fails. Let's go to our documentation. And generates a double with result. Must specify the input data types as signed or unsigned. Well, that's the vector stuff. So much stuff. Let's store. maybe this is this. Okay. Arithmetic. Add, sub, compare, multiply. Oh, no, multiply. There we go. Yeah, you get multiply add sort of for free. Multiply. I don't know how they deal with that. This should probably tell us. Okay, so 64-bit variant is equivalent to this with 0. Okay, interesting. XD, XN, D is destination, N is one multiple, and then M's the other. Let's look for overflow. I'm kind of wanting to not worry about it. No, that's not right. Floating point overflow. Yeah, so I mean, it looks like there is something we can branch on, but we've totally not defined in exceptions or anything like that. But let's at least make a note about that. Well, it's not just multiply, is it? Right? I mean, add can overflow too. Okay, but I think we'll leave it there. Multiply is just multiply. Multiply by BA is product. Okay. NE. Let's check that vocabulary list again. So, okay, they check. Oh, they don't really have a not equal. Well, let's add one. Okay, we'll just add it as a symbolic thing, and we'll call it NE. I guess we don't need the name of it to do the work here. All right, same kind of thing. This is sort of a new category. Global any, maybe NEQ. Is that? Not equal. Okay. So we have that. It pops two things, so it's kind of similar to this. Well, if it's jump if true, it depends how we want to handle it, I guess. If it's jump if true, well, I guess, do you want to just write multiply, or do you want to do multiply and then you do a jump if true on something? If the product and the status maybe, or something, if you want to execute it at that level. But if you just wanted to say like, this is a fatal exception, let's just bug out. I think we don't want to make it exposed at sort of the user level, just make that a kind of a crash, I guess. NEQ. Oh, no, NEQ is just, it's like a relational operator that pushes a truth value on the stack. Okay, so let's get him. Okay, data stack x0 x1 temp has part 2 has been pushed 1 if equal else 0. Yeah. Okay. And we'll make it subtract, and that should be wrong. Okay. I think we can test. Well, it's pretty close. Okay. NEQ false if values differ. Okay, so we're going to push data plus 8, so 142 versus 58. We'll call NEQ. The top of the stack should be a 1 because they are different. Whoops. Yes. And I don't. Okay. Test should fail. Ha. Okay. Except 1 is the wrong thing, isn't it? Oops. NEQ is true if values differ. doesn't change anything really. All right. Core. Okay. Neg pushes them. Well, let's assume, well, I know we have to do a compare. Compare x0 to x1. All right. And then I think we did B and E before, right? Oh, here we go. BEQ. Okay. If they're equal, this is, well, LA values equal. So let's move x2 gets 0. Or we want 1. It's hard to figure out the right. Let's assume it is not equal. Okay. If they're equal, if they're not equal, well, this is really any cube push. All right, so we pop x0, x1, x0. We compare them. If they're not equal, well, we've preloaded a 1. We're assuming they're going to pass. If they're not equal, we jump forward and we just push that x2 value. If they are equal, we reset x2 to 0 and push. Push the 0 instead of the 1. All right. I don't know. I don't think there's an instruction sequence to get a truth value there. But, all right, let's see if we got it backwards or forwards. All right, Nanny Kitchu. Okay, then we need the other test. Well, I jumped ahead a little, I guess. Well, this test is NEQ false if values the same. Okay, same deal. The only difference is how we're pushing. Okay, so last time we pushed 2 different values. This time we'll push 2 the same. And we expect a 0. And this should pass. I'm confirming that it does. Okay. I guess we strictly could have just hard-coded a 1 return before and then added our conditional code, but I'm not going to worry too much. All right, support NEQ. Good. All right, that leaves one more? No, that was it. Now, this is gonna get tricky. All right, I think we're gonna make it. Oh, did I? I did add those. Okay. Let's. Well, test start. Recursive factorial. Okay. Now, let me get that sample. I don't know why this. I guess they don't have real tabs anymore. I just feel like it will be simpler to have this here. Oh, these I probably could have. Okay. Yeah, let's take a break before we do the real thing here. Yeah, let's just take our break right now. Okay, see 3 or 4 minutes. See you then. Yeah, always lose the indentation. All right, welcome back. So we're just going to do something very similar to this. We'll have to build a dictionary and a secondary is our range. Okay, so test dictionary we can do. You know, I think it might make. Well, we always have this, so let's make it 0. Yeah, I was thinking in break, like, could we find a way to put, like we use the address label on the secondary calls, but we have to put the index on the others. I just don't see a way around it. Yeah, I don't see an easy way around it. It will go away once we're compiling things for us instead of manually compiling them. Okay, so our setup is going to need dupe. Well, it's going to need push, but we'll put them in the order we got them. Add dupe. Make that 1. Push for the number is 2. Well, any dupe 1 sub multiply. Dupe, oops, push. Any Q. Change the name. Zero, 1, 2, 3, 4, 5. That's 6 times 8 is 48. I think we reserved 80, so we're okay. All right. Now the secondary, we're going to make a factorial It can be local. All right, but let's steal this. Okay, L factorial. And then this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, let's just make this 16. Give us some room. Okay, and so L factorial is going to use the start dictionary, and it always uses start to D. We could almost make that implicit. Do I need for the if check? Oh, yeah, right. Div 1 NEQ if. Okay. All right, so the calls, well, dupe 1 NEQ if dupe 1 sub factorial multiply. All right. And entity. All right. So our first call is dupe, which is 1. Dupe. Our next call is push, which is 2. And then we have to have the data. I think we said secondary data. One. NEQ is 3. That's just logical, but if needs to. And this is jump if false, which we didn't add. I guess I'm going to go out of order. No, that sounds like bad luck. Jump if false. What did I just delete? If. Oh, yeah, we don't want if, we want jump if false. Okay. And then that has to have. Well, I don't remember. I think it was in here. If 0 does not jump. Okay, secondary target. And we don't know the instruction yet. Okay. Jump, that's if jump if false. Then we need to duplicate again, which is 1. And a 1 again, which looks like that. I don't think that's right. Dupe, push a 1, sub is 5. Then factorial, well, that's interesting, right? That's the one we're defining here. Okay. And so this is a call to factorial. And 6 is multiply. Yeah, target. Okay. And then this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oops. 1, 2, 5, 6, 8, 10, 12 is number 13. And that's our N2D. Okay. Do we believe it? Okay. Dupe, push 1, NEQ, jump if false down there. If NEQ says false, then they are equal to 1, so that's good. NEQ false, jump if false down there, duplicate, push 1, subtract, factorial, multiply, N2D. Okay. Woof. So the act is really just calling the interpreter. And that's this. Run interpreter. And then, oh, we have to push first. What do we say? Not core assembler. Data push a register. Okay. So let's see. Let's go for 5. We'll move x0 is temp, gets 5, and then we'll call data push x0. Okay, so we got 5 on the stack. Then we call factorial. And at the end, let's do data pop x0. 5 factorial is 120, if I recall. Move x1 gets 120. BLS assert equal. And I'm trying to do lowercase instructions and uppercase macros. All right, 5 on the stack. Call run interpreter is going to clear the stack. That's not going to work. Grr. Maybe run interpreter. Well, that's a big change, right? No, I haven't run it yet because, yeah, we'd have nothing on the stack, and that's just going to ask for trouble. Um, I'm going to do it this way for now, but I think we really probably need to not initialize this in here, because I think in the case where we have the whole system running, you theoretically could just, I mean, it's REPL style thing. You can just type in a commands, and then you'll have stuff on the stack, and then you can call methods, and they should not reset the interpreter or anything, reset the stack pointer. Now this part, this is how you get started in the first place. That seems okay. So I'm going to do that. Okay. We do have to work this out at some point, though. All right. Um, now we do our make. Okay. It just means we're so good, right? Let's check a different one. 6 factorial then is 720. I believe I did. I added that during the break. Recursive factorial. Oh, and it's right here. So yeah, we called it. We're allowed to have it work like this. This is, this is the way it's supposed to go. Not everything has to be debugged for 2 hours of tracking through binary data. Okay. And I think we've done everything right to do it. Let's mutilate and start 2D and make sure. So my guess is if we did not do this, we would screw up. Okay, so let's do that. Bloom. Yeah, that fails, and we blow out. Because this is just like when you call a procedure, you push the program counter on the stack, so when you return from the procedure, you can pick up where you left off. X20 is our program counter. If we don't push it on the stack, then wherever they are in their progress is going to be where we jump back to, and that can't be right. So I think we're good. And I put this down to mostly that we got these macros defined is good. Maybe we could mutilate sub or mul. Let's mutilate mul. Let's say we called sub instead of multiply. And then we're going to get some other random value. Did I take that back out? Oh, no, I didn't. I don't think I cleaned that back up. Okay. Yeah, so we can't tell what message it was, but yeah, I mean, it may be that, well, I mean, it's intended to work because our thing calling secondaries needed this line too, so that seems okay. All right. But I mean, yeah, sometimes it's shocking when it passes too quickly. All right. Let me make a clean just to make sure everything is good. All right. Nice. Okay, now I don't know if there's another variation on recursion that would screw things up. I think we're okay. Yeah, I mean it happens. All right. And I mean I wrote this just on a little tiny half a file card because but when I wrote it, I kept track of the stack very carefully, and I think because I did that, I didn't have to debug the routine itself. We got the routine encoded correctly or written correctly, and then the encoding we've been beating on the last few days, so it's finally doing what we want. So we're good. ACP check that recursion works. All right, now it will be a little tricky when we're compiling, right? We have to make sure, like, when you compile and you call a secondary, you look up that secondary in the dictionary. So we'll have to make sure that as we're building something, we put it secondary in the dictionary as well before it's completed building. Okay. So yeah. All right. Gosh, I feel like we deserve another break or something. I already drank my water, so I can't celebrate. All right. Wow. I did not expect to finish this today. I was worried we might not even finish. Well, I thought the Refactor dictionary would take like half an hour longer, and that we would kind of just get this ready to roll. But I guess I'm happy. All right. Well, so what that means is I didn't really do the dictionary stuff. So I guess the deal is what's left, and let me just add a slide to fill in here. Okay. Or maybe it's kind of what's next. And I haven't decided what order to do things, but I think the next thing to do would be build the system dictionary and build the user-defined dictionary. And we kind of need those to do compiling, so I think that's fine. We need to, build the compiler, which is tokenize and generate code, I guess. And that uses the dictionary. I guess I could put that dependency in there. To write the actual outside environment, the REPL, we need to be able to read from keyboard. I mean, it's not really the keyboard because we're going to use system calls that I hope will work. And then we need to build the outer interpreter, read eval print loop kind of thing. Okay. Yeah, I need separate dictionaries. Well, maybe. I'm not sure. Yeah, I think it will. I mean, basically, there's going to be a block of space. It can't, because we can't do that relocatable label thing. I have to put that space in data and then backfill the actual addresses, which is really, really too bad. I mean, maybe I should dig out that assembler reference. Maybe we should take a look at that relocation stuff, because if we could figure that out, it would simplify the system dictionary building substantially. All right, but build the outer interpreter. I think that would do it as far as, and then we got to build out the primitives. Arithmetic, logical, conditional, etc. Okay, and once we have that, I want to, we need an assertion library for 10th, and we need to build a game calculator or something else small. I don't want to spend a ton on it. All right. So I think for building the system dictionary, we'll take a little time. It's 3:45, so we got 45 minutes. I think we'll take a little time and do the research and see if we can figure out the relocation thing. So we can build if we could figure it out completely, I think we could build this thing statically in the text segment as constant data. And then the user routine is going to be a second block. And as you're compiling it, you're going to fill in those slots, put in a header, fill in the slots, next header, next slots, and so on. And the first one will point back to the system level dictionary, the last entry of the system level dictionary. Okay. I think that's a good plan. Let's draw a picture of the dictionary. Do I have one that's good enough? Well, we're going to modify it, so we definitely need to start somewhere. Yeah, this page is probably good. Okay, now I think I'm debating the order, right? Because the routine, well, if the name is there, then when you come in, you just look at the name. Otherwise, you increment to the link. Yeah, that probably can work. Okay. Yeah. I'm thinking this will be 8 characters. Is that 8 bytes? Well, that's really only 7 if we make it null terminated, which I think we might want to do. We don't have a string EQ. We're going to do that. Name of the routine. I mean, the alternative would be 16 bytes with 1 reserved for the null character. The link is going to be 8 bytes. The address, everything else is 8 bytes, except the assembly code could be whatever it is, but it's divisible by 8 because it requires it to be 32-bit. Or divisible by 4, I guess. Okay, and then the other side, same size header and lots of 64-bit entries. Okay. So let's do that research. Let's see. I'm going to hide for just a second. Sorry. Okay, I've got a couple articles. This one I think is the one that's going to do it. Okay, so this is ARM64, but notice what they have here. Hard to read, but LO12 is the low 12 bits of an address. And then this CBI pattern, I'm not sure what that means. Okay. Start this. Yeah, okay. In order to keep track of symbols, ELF, which is the linker format, basically. Extended linker format? I can't remember the name for it. They keep track of address of reference. See, what I don't know is if you can do this in assembly code. I mean, in data. I missed completely need for... Right. No, I understand that. I guess he doesn't. All right. Yeah, because you got the 12 bits, just like we do the page and the offset in our load address. Let's pull that up. Right, we do add page. That's a modifier that gives you the high bits of a thing. And then add page off is the offset, is the low bits of it. Now, which ones are 12 and 20 and all that, I don't know. But adder P is going to have, probably has 20, and this probably has 12 or something like that. Okay. Now, let's see if we get any more. Right. Oh, I guess he does understand. Okay. Yeah. Okay, so there we did the same thing. ADRP loads that, and then they're doing a store with that plus the low 12 bits. Okay. And that's really probably, well, yeah. I mean, we're going the extra bit to load the whole thing into a register, but depending what you were doing with it, you could just use that low bits. Well, this let's see, 30, is it 30, 20 and 32? I'm not sure how many ADRP, but the 12 bits is, 12 is 4096, right? I think you get access to like 4 gigabytes or something. It's a lot. I think, is that 32 bits? So a 20-bit ADRP location and page is 20 bits and location is 4096. If I'm doing my math right. So I don't think you'll just need that. I mean, you kind of could. Well, it might be a squeeze to get our headers in 4096 for our system stuff. I mean, because that's, 12 bits. Everything is 8 bits wide, so you got to take, it's only 9 bits really, which is 512. So I don't think we're going to have, I mean, you need multiple words. You need the name, the dictionary address, the word address. Those 3 at least have to be there. So you got 3 words for that. So 512 divided by 3 is, less than 200. You might squeak it in. But then you'd also have to make sure that, like, you knew that you were looking in the system one and you had the offset for that. It wouldn't be very symmetrical. Yeah. So actually, I got to remember how they do this. Maybe it's not. Yeah, it might be pre-multiplied by 3 bits or something that you get. Because these are known to be locations, they know they have to be in code is 32 bits. The code words are 32 bits. So, and they're aligned to that. So is that 2 bits on the end or 3 bits on the end? 32 bits is 4 bytes, right? So, I'm not sure, but it is multiplied by something. And there's also some weird thing that, like, system routines will have odd addresses or something, and then they filter that off or something weird. But anyway, but this at page is exactly, at page off is exactly the same as this £:low 12. What I don't know, well, let's try it. £:low 12 : and then let's take off the page off. Doesn't know it. Oh, Okay, this is a bad sign. Okay, let's put this back. Okay, so that's telling me they don't support these. But where did we find at page, right? I mean, that's that's kind of weird. Okay, ARM documentation. So this is the CLang reference. And somewhere in here is all the variations. Yeah, there's lower 16, upper 16. That's for AR32. This one we have 12, 63 to 48, 48 to 30, 47 to 32, 31 to 16, 15 to 0. Global table offset entry. Okay, that's the 32. So I think if you took, I think it's going to be 2 empty bits on the right, then 12 bits, and then 32. So I think you're getting, well, that's 44 plus 2, I think, bits. Yeah, unfortunately, we cannot create a table like that. What happened? Well, maybe we got to double check, but I believe we tried it. I think what it did was it took the offset relative to the object file itself, not the global offset where it would be once they linked all the object files together. So it did not work, is my understanding of what we did. Now these don't look that great to me as far as like what we want, except if they understood it. Well, now maybe we haven't tried this. Yeah, let's do an experiment. I think we'll just put something in core tests, and we'll make up. Oh no, we had something for that. What was that called? Core unit test demo. Okay, I think this will give us a place to try. All right, so test all. That's fine. Okay, so we're saying we would like to do. Well, let's be explicit. This is text. Okay, so what I would like to do. Well, no, I can't get the 64-bit value. But we can find out, I guess, something. Okay, so this is test globals. Okay, what we'd like to do is put a quad, and we got NL as an extern. NL. These 12-bit things are just killing me. Well, let's put something in here. Let's do our OX feed beef. Okay, because we want to be able to find this thing. All right, now we're going to put NL at page. Can I do that? Will it relocate it? I guess we don't need anything in here. Okay, and then let's do page offset. Yeah, let's try this. Okay, well, unit test demo. Oh. this is at page off. Okay, and it did the unit test demo. Why do we get a space here and here, but not one here? Print number maybe is doing that. All right, so let's look at unit test demo. Well, let me be more careful. Make sure we get exactly what we're getting into. Feed beef. Yeah, there's just nothing there. Oh, this is disappointing. Okay, we'll go back and there's another section for this. Maybe that's... No, that's the start. Okay, section text. There's my feed beef. 0000000. Okay. Yeah, I think we're... I mean, that's 64... Sorry, each of those is 32 bits, right? So we're not getting any data in there. And that's linked. So yeah, I think this is not working. But I would love to find explanation of this. Maybe there's something else that we could do. Back here. All right, we've looked at this guy's stuff before. That's okay. Not a lot of stuff here. Yeah, that stuff's not really it. Okay, this is what we looked at before. This is... Yeah, we can't do that. Not relevant. Okay. Let's just flip through his pages and see if there's something he did. I think we got the page offset stuff from here, actually. Except move X1, X2. Yeah, he's got this. More page offset, nothing in the data segment. Not the vector stuff we're not going to look at. All right, let's just take some quick looks. It's all code. I think these are minimal examples. Okay, a little data, but we know how to do ASCII Z. Message bytes and ASCII Z's. How to see an infinite loop. Okay. We don't need them for that. Okay, here's some actual data. I don't see anything. It looks like a page. He's doing the page off thing there. In code, not in data. I don't get the feeling we're going to find this here. Some macros. We pretty much saw that before. Oh, some nice little macros. Yeah, so this is their defined, but it's very restricted. Let's see, how can we find that? And mostly we've been looking at GNU documentation, so I have a link somewhere to that. That's this. No reloc. One match. Stab D. Oh, symbol table, something debugger. Symbol tab table, debugging. Symbols. The name of the symbol is generated even. Symbols file set to the location counter relocatably. Yeah, that's. There's a whole thing around setting up debugging information. So basically when you link a file for debugging, you build up this table of symbols and all that stuff, and that's what this descriptor is doing. But I don't think that's going to give us relocatable labels. And I did read through all of these at one point and didn't feel like we had anything there that would do it. Difference. Okay, we don't have to deal with that, thank goodness. All right, I don't think that's going to do it. Okay, so I'm disappointed, but in some sense not surprised. Everything we've seen so far is kind of showing we can't do that. I really wish this would take registers. I would love to say, VSP is X19, and then just use that throughout would be great. No, I don't think it's unusual either. That's why I'm very puzzled why it's not, why we're not seeing it. If you compile C++, right, you build those little descriptor tables for how to find their routines and stuff like that, and they have to point to the version of each function for this class compared to its parent or child. So, I mean, I wish I knew. I mean, it wouldn't surprise me if they have something, but I'm just not finding the manuals for this stuff. I mean, it seems like they basically want to discourage people writing assembly code, which I kind of understand. I mean, if you can write C code, you're, 95% portable or something. If you're writing ARM64 and they come out with the M17 that's, too different, then you have to throw away that assembly code and you're stuck. But I don't know. It really bugs me that we can't do this. I worked at Digital years ago, and they were big on using a language called Bliss, developed at Carnegie Mellon by Bill Wolf. And it was a little weird to use it because it wasn't really typed per se. I mean, you could reference something that was an int and grab parts of it and throw it into something else, and it wouldn't give you any help there. But it was a really good optimizer. But the real thing for it that made it great for the compilers and operating system stuff, you basically had a compile time language that would fill in tables and all that stuff for static data. And definitely tables of references is common, it's, we basically, when we built libraries, we always had a little jump vector inside that would point to the routines in the library. And then if you wanted to use it, you would copy that jump vector into your data area and reference things through that jump vector. But if you needed to patch one for whatever reason, you could, replace a function or something. You could just replace the entry in the vector function or the vector array. That sort of creating a list of references is part of that. If you don't have that, you're doing what we're doing, which is running around at runtime and backfilling things in. Now, maybe we're close. Okay. Maybe it's time to get serious about the dictionary. Oh, okay. Let's go back here and take our picture. So I guess you got your header, 8 bytes link, 8 bytes address, and a bunch of bytes. So sort of 16 bytes overhead if it's 8 byte names. And I don't know, that will probably cover most of it, but not all of it. I mean, factorial, right? Factor is 6, 3 more is 9. Okay, but what I want us to do, so with our setup, we don't need the header area to be next to the code. So the normal way you would do this, I could make a label for each entry, and then the link to previous can point to that, and address of code can point to this. But normally, I mean, if you were building it up, you would write the routine name, write the link, write the address of the code, fill in the code, and it's all right there. But for us, we're going to say the code's going to live somewhere else because the code is a pure compile time constant kind of thing. The table structure is not. We're going to build that at runtime because we can't build it at compile time. I mean, if we can figure out a way, I'm happy to do it. But for now, my working assumption is we're going to allocate a block of memory for the dictionary, and we're going to pre-populate in all the system routines like mul and sub and all that stuff. Those routines are going to get put in here, header, 3 3-word headers. And then at the end of that, that's going to be like that next address can be the first one for the secondaries. Now, Forth has this notion of multiple namespaces and stuff like that. We're not going to try and do that. So I think in this sense, we can just build it. So I think with what that means for us, well, because these are fixed size, if you don't need the code there, then we can work out what's the link to the previous. Well, it's three words earlier. So we can fill those in runtime pretty easily. Just 0, 3, 6, 9, 12. Going down. The name we're going to populate in there. And I think we could just put the name. The name is a constant, so that can live in the no. Yeah, I think the name. We'll make sure it's 8 bytes. Okay. And we're putting the bytes directly in. But I think our dictionary start could say the name. Right? Because the dictionary is being built in a data area. Do we try creating reference quads in the text section? Yes. Yeah. I don't know if I took it out yet. No, I did not. So this is text, and that's the section. That's the stuff that wouldn't work. However, this should go away. Okay. Right. So let's add our dictionary start. Let's look at that code. Where is that? Well, this last interpreter test is a good example of what we're doing. Yeah, so I'm thinking we could put the name of the method maybe after the test dictionary, because they all have to share the same dictionary. Test dictionary is in the data section. All right, we could say give us the name and put that in a quad before, or in one of the words. Yeah, that would certainly be legit. And if we were doing this for a real language, I would probably do that. So make that first, make this word a pointer to the name, not the name. But I think for us, I'm just going to take the expedient way and put the name in. I mean, I feel confident about how to do it, so I'm not too worried about the limitation. I mean, I could certainly go to 2 words, which would be 16 or 15 character names, and that's pretty reasonable. I mean, where this grew up, right? It was, like Fortran used to use 6 character names and stuff like that, So, having giant names is it's useful, but it's not absolutely critical. 7 characters is a little better. Maybe I should just do 2 words and just see how it goes. Then it's 4 bytes, 4 words for the header. It's a lot of bytes. I mean, it's not. I've got gigabytes on my system. What do I care, But I can't help think of these little microprocessors where they were doing, 3 bytes and the length. So that's 4 bytes of stuff. That they would. So if you did factorial and facing, they look like, well, you got to find an 8-letter word. If you did facing and factor, they both look like the same word, because all it stored was 3 FAC. but yeah, 15 characters. We won't care about that. We're not going to write giant test names or something. It won't. We don't have to. Okay. Yeah. So we'll do 2 bytes. 2 words. 15 characters. And then this is 8 bytes. Yeah, I guess we'll say B. And this is 8 bytes. Maybe I should just call this 2 bytes. 2 bytes. Okay. 16 bytes. Multiply better. All right. Yeah. So let's add an argument that takes a string, and we're going to make that, we're not going to mark it ASCII Z, we're going to mark it ASCII. And you got to make sure it's got 15 bytes. And the last one you care about is 0. Okay. I think that's doable. So dictionary, it's really the entry, right, that needs it. Now, underscore push. The other thing going on in my mind is there are some words that are used by the system that aren't really part of the user's vocabulary. So push is one of those, because when you, go to our factorial, you say 1, it's just a literal sitting there. Well, it turns it into push followed by the literal. And same for if. It turns into jump if false followed by an address. And I don't know, any others that did something funny. But dictionary add, I guess if I took the name you want to record it by, now the real thing here is we're not going to look at the name when we do stuff like this because we're just using the index. But we could require it. Or you could say this is a system routine. It's got an empty name. That might be better. Yeah, that's the system name. I would love a way to tell how big these strings are. But I don't think I have anything that does that. All right, but let's just say the system name for this. I'm going to say system names, ones you don't use yourself, would not normally have underscores. Okay, N2D/0 1 2 3 4 5 6 7 8 9 10. Well, 8, and then 1 2 3 4 5 6 7 8. Okay, so this is 1 2 3 4 6 7 8 16 bytes. Okay. Now, dict add is in assembler macros. No, it's not. It's in core macros. I think there's a way to. I think you can put default arguments on your names. Gas macros assembly. Load string. Now, we don't support a lot of this stuff. Name colon rec. What does that mean? Oh, vargs. Okay. Ugh. Oh, yeah. Okay, you just say equals no value. Okay, so I think we can do name equals 0, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. All right, so this is the default name. And I don't put a 0 followed by a number directly because then it gets confused. But 1, 2, 3, maybe I should make this 3 different characters. Plus, times, divide, subtract. Okay, maybe I better swap those two. Yeah, plus, minus, minus. Okay, so this is just a dummy name that's going to get written. Oh, now dictionary entry. This is the code that generates the directory, the entry at x0. I'm not sure where we're writing this. Okay, well, I guess we'd have to put it in the data section. And we're going to put, what was that thing to generate addresses? There's all kinds of little macro tricks. No. Was there assembly? AS unit? Yeah. Oh, no, that's not it. This, \hat. Okay. Let's do L. Entry at colon dot ASCII name. Okay, so we put that somewhere. No, I don't think this is going to quite do it. All right, this so far, let's make sure nothing's broken and then we'll call it a day. Okay, I think it looked like it ran everything. All right, so I'll just say start revising dict add to take a name. Okay, well, we'll stop there today. Tomorrow we'll pick up trying to create, I think I want to be able to, what I'd like to do is modify that macro, require people to put the name, and then make the macro write the name somewhere that we can get to it. It maybe the name ends up being in there twice or something, but that'll start us out. I'm trying to drive this current macro towards the structure we're after, and then we can look at patching it and stuff. Okay. Well, thanks for joining today. We made some progress. Some of that went nice and quick. That was great. And I'll see you tomorrow, hopefully, 2 to 4:30 Eastern, 7 to 9:30 p.m. UTC. And have a good evening. Thanks. Bye-bye.